now. Okay, so welcome. Just a quick review, although it was just on Monday, so we don't need to talk about it too much, right? But we ended on talking about just being able to identify outliers, right? And so we talked about two different ways that we can identify outliers. We established two ways to identify outliers. Okay. Looks weird with a colon and a colon, but anyways, the first one was that we could use a Z-score. Remember, a Z-score is the standardized value. So it takes the distance for each point from the mean and gives it to us in terms of the standard deviation. So how many standard deviations away from the mean is some value. So we can use Z-scores, which are standardized values, right? Where anything below the mean is going to be negative, where negative values are below the mean, and positive values are above the mean. Okay, so just as a note, Z is X minus, and I think we used X bar. Let me just refer back here. Hey, this fly just won't die. I've got this fly that just wants to, maybe I smell bad. You guys will never know. Oh, right. So let's see here. I just want to bring up the, here's the formula that we had for the Z-score. Oh man, hey. So slow. Come on. Typically, we just use mu and sigma instead of X bar and S, but technically here we are using X bar and S, X bar being the sample mean and S being the sample standard deviation, right? And so we're just seeing how far is this observation X1 or X2 or X3 or X4 from the sample mean in terms of the standard deviation, right? And so any Z-score, I'll move this over here, any Z-score beyond plus minus 3, right? So in either direction is considered an outlier. Now, the second option is the 1.5 Iqr rule. So the 1.5, using the 1.5 Iqr rule involves, well, first finding the interquartile range. Remember the interquartile range, the Iqr is Q3 minus Q1. Most software will give you the quartiles, right? And so then you can use those to calculate the interquartile range. So Q1 is the point that separates the lowest 25% of your data from your highest 75% of your data. And then Q3 separates the lowest 75% of your data from the highest 25%. So it's considering the distance between the middle 50% of your data. Ooh, okay. So the interquartile range is going to be Q3 minus Q1. And you can find those by hand, but I would recommend just using software. And then the 1.5 IQR rule says that you have a lower bound that's going to be Q1 minus 1.5 times the interquartile range, right? This essentially says move down a distance of 1.5 times the interquartile range from Q1. Yeah. So in terms of, we saw a box plot, and I'm just going to draw one here on the side. If we have something like this, here's the median, here's Q1, and here's Q3, because we assume that we have some scale here on this side, kind of arbitrary scale. Then we want to move down. Oh, I'll use a different color maybe. How about that? Right, then we move down a distance of 1.5 times the interquartile range. The whisker, so this is called the whisker, right? The whisker is drawn at the data point that's within, so the last data point within the 1.5 IQR range. And then anything beyond that is drawn as an outlier using usually an asterisk or a dot or whatever the software has chosen, right? And so kind of visualizing here, to get to this point, right, I have to go Q1 minus 1.5 times the interquartile range. Whereas if I want to move up, right, I'm kind of up because I'm using the y-axis, up from Q3, then my upper bound is going to be Q3 plus 1.5 times the interquartile range. Okay. So then the upper bound is Q3 plus 1.5 times the interquartile range. Okay, which really just says move up a distance of 1.5 times the interquartile range from Q3. Right, there's symmetry there. Why is it 1.5? Pretty common question. Everyone's like, why 1.5? We're using Tukey's rule. So he came up, he proposed this, and lots of values have been proposed. And this is the one that we kind of have adopted because it's a nice trade-off of being able to identify outliers. So imagine if you used 3 times the interquartile range, you don't even need to use the interquartile range, but let's just say that we're going to stick with that. If we use 3 times the interquartile range, then we're not finding as many outliers, right? And then, but we want to allow for some range that's not considered outliers. And so you could probably write a thesis on some other proposed value, assuming it hasn't already been done. I promise all that low-hanging fruit, it's all gone. So someone has written a thesis on probably every single value, but the one that we use is 1.5. Let's just, yeah, there's your thesis, your new statistics thesis. The 1.52344 rule, IQR rule. Who knows? It could work. Maybe it's good. Maybe it's significantly better than the 1.5 IQR rule. Who knows? But anyways, so it is kind of an arbitrary number, but it's the trade-off game. So then here I'll draw this. Oops, keep messing up my R. I think the fly flew into my hair. And often the flies, they die after some time, but there's been 2 in here that are just like thriving in my house. in this
really
environment.
like data science.
Yeah, they want to stick around. They're like, isn't data science 300 yet? Yeah, just like you guys. Anyways, very distracting. I'm sorry. For me, mostly. So anyways, so we have two ways of identifying outliers. Why is it so important to be able to identify outliers? Makes it enjoyable. Yeah, me going like this. We have to be able to identify outliers because outliers are either really important or they've been entered incorrectly, right? Either way, we're interested in outliers, right? And so we are always interested in outliers in our analyses, right? That's because they could tell us two different things, right? And either way, we're interested, right? One of them is more interesting than the other, right? So scenario number one, it's a data entry error, right? That's bad. That needs our attention. Okay. So it could just be something that you kind of see and it doesn't make sense, and where did it come from? Or and it does require some knowledge about how the data was collected and things like that. But the other option is that it is a truly extreme value, right? And so a truly extreme value that we want to, I'm trying to not say that needs our attention, right? But essentially in our analyses, we're interested in those extreme values. How did those happen, right? Usually we're not concerned so much, oh yeah, everyone's doing this. We want to know about these extreme values, right? And so a truly extreme value that should be looked into, right? That we should analyze further. So there are kind of two ways that we can get outliers. I can't think of any more, but if you can think of another way that we could have outliers, let me know. But those are kind of the core ways that we do, right? We'll talk a little bit more about what do we do if it's a data entry error. We have a couple of options. We could remove it. We could change it to something more reasonable if we have kind of an idea of what something more reasonable would be. Often we just end up removing it because we don't want it messing with our data and our analyses. Okay. I'll call that the end of our review. Kind of a long review, but it's important. So especially long because I think I started with, we're not going to do a review, but here's some important things to talk about from last day. So anyways, all right. So, oh, this caught my eye, but we already talked about it, and I'm happy with what we said, right? In terms of outliers here, it looks like we have one outlier in Groton, whatever neighborhood that is or community that is, I don't know, doesn't matter. But that's the only one with an outlier. Now it looks to me like this might be a small data set because there's this beautiful symmetry and there's an outlier that's relatively close to the rest of the data. But it's, again, something that we would look into, right? So I'll leave that there. And today I want to talk about, we're going to finish chapter 2 today. Copy. I don't really know how to make my iPad faster. Anyways, it's not meant to be fast, maybe. Who knows? I need to get the Pro. Maybe that's the problem. No, I'm an Apple-only household. I refuse. Anyways, so let's talk about, so we've talked about just one variable, right? One numerical variable, one categorical variable. Now we want to talk about just the relationship or the association between two variables, right? And so we can talk about the association or relationship is usually what I call it. Okay. And so this textbook loves calling them charts. I would call it a scatter plot, but just as a side note, a chart is a plot, which is a graph, and we can use, you can call it a scatter graph, scatter plot, scatter chart, it doesn't matter. And that applies to all the charts that we're going to talk about. Okay, so just in general, just be a little bit flexible with the terminology there, because I'll probably slip up and call it a scatter plot. There's also a really fun package in R that makes a scatter plot. So a scatter plot looks like this. I'm kind of assuming that you know what I mean when I say scatter plot, but maybe not, right? It maps the relationship between two variables. In this case, it maps the relationship between the high temperature and the sales, right? And so in R, someone decided that we needed to be able to replace the dot with the outline of a cat, making it a scatter plot. Pretty funny. And so you can look into the scatter plot package and play around with that. There's some default code that you could just run, and it should just run. And maybe I'll dig it up. I'll dig it up and show you guys, because it's really cute and really funny. So in terms of the data here, just so we are able to start to recognize, you know, what our data looks like versus what the data that they had looked like. So here, the data that we're looking at right now is the data for bottled water sales at Queensland Amusement Park for a sample of 14 summer days. So we don't actually know which 14 days. Are they consecutive? Are they not? We don't have any of that information, so we're going to have to ignore it, of course, but that would be something that we might be interested in later, right? But we don't have that information, so we can't consider it. So here, we're just focusing on the high temperature in Fahrenheit and the bottled water sales measured in cases. Right, and so we had to decide which one is the response variable and which one is the explanatory variable. Okay, so the response variable, and now I'm drawing a blank if I have talked about the response variable with you guys. I definitely have in my other class, but we need to decide. So the response variable, is the variable of interest, right? And so it's the variable that we're most interested in, okay? The variable of interest, right? And how does it depend on another variable.
I was going to say dependent variable.
Sorry, say that again.
I was going to say dependent variable.
Oh, yeah. So nice. Okay. Thank you. So it can be called the response variable. Sometimes it's called the dependent variable.
The term dependent variable is more familiar to me.
Yeah, so it totally depends on what field you're from. So if you're coming from like a biology field, they like dependent, independent. I like response and explanatory, and I'll show you why I like those. But they mean the same thing. So the dependent variable is helpful because it kind of nudges us in the direction of how does it depend on another variable, okay? And the response variable or the dependent variable is always mapped on the y-axis. Mapped on the y-axis. Okay. Whereas the explanatory variable,
Or the independent variable.
Yes, but I didn't do the X thing, no, with you guys.
Yeah, you did.
I did. That's why I like the explanatory variable. No.
X.
But we use them interchangeably, and so you need to have a handle on both of them. Unfortunately, so the explanatory variable is sometimes called the independent variable, but because that doesn't tell me which axes it goes on, I prefer explanatory. But a variable that might explain changes in the response variable. And it is mapped on the x-axis. Right? And we already talked about, okay, the x-axis, you've got a little guy going down, he's down low, he's no. And so the explanatory variable or the independent variable is mapped on the x-axis, okay? So, and you can have more than one explanatory variable, whereas you typically only have one response variable. So you only have one variable that's involved in your research question. Everything else is just trying to explain changes in the response variable. So in this case, when we have the temperature and the bottled water sales, right? If we think about which one would impact the other, right? Then it makes sense that we have, okay, the sales would be impacted by the temperature, right? And not the other way around. It's not always clear cut. There are scenarios where you could put either one on either axis, but for the most part, right, here, we can't change the sales that we make to change the temperature, right? But the temperature is going to impact how much we make in sales, right? And so here, this would be our response, since it may be affected by the temperature. Okay. Good. So scatter plot, right, is really just a visualization between two numerical variables, right? And so, or I guess we're calling them quantitative. Another one of those dual names for the same thing, right? And so sales is numerical or quantitative, and the temperature is also numerical or quantitative. And so here we've mapped these two quantitative variables against each other. So that's how we typically use a scatter plot. You can use a scatter plot, but it's kind of weird. You could potentially have a categorical variable on the x-axis. But for the most part, we're talking about two numerical variables, right? Or two quantitative variables. Later on, what we're going to get to is, okay, we'll look at the scatter plot, right? To be able to kind of look at the relationship between two variables, right? And then we're going to look at the relationship itself to determine an appropriate model, right? How can we model this behavior? So we don't want to be looking at these individual dots anymore. We want to have an overall model that is going to capture this relationship, right? It's going to be built off of these points, right? But later what we're going to do is we're going to build a model. And here it looks like we could model this with just a straight line, right? And so that's our most basic model, and it applies to most scenarios. And so then we're going to build this straight line, this linear regression model, to try to capture all that activity, right? And so we build it off of data, but then we can use the model for future observations, right? Especially if you're if they're predicting temperatures up to 92 degrees and you're in charge of ordering water, then that would be useful to know, right? Okay, then I should probably have at least 30 cases on hand, because that's typically how much we sell, maybe a little bit more, right? And so you can use those models to make predictions, but we're saving that for just a little bit longer. Okay, so I'm going to remove this line for now, but that's where we're headed. Okay. Good. Okay. So we can measure the relationship between two variables. Okay. Oh, of course, hang on. Bring it up here so I can have it on the same page. Okay, so the covariance is a numerical measurement of the linear association. Okay, so this means that it must have a linear relationship, must have a straight line relationship. Right, so straight line is really, we can just say linear relationship. Okay, so the covariance is one of the ways that we can measure the n-1. There's that pesky n-1 again here, right? I'll just talk about this a little bit and then I'll talk about it. But it's basically one of those things that we just accept it. So yeah, I know. Not the best, right? When it's like, well, that's what it is. But so the covariance is going to be a numerical measure of the relationship between two variables. It's got one major downfall, and that's that it depends on the units of X and Y, right? And so the covariance we denote by S subscript XY. So where X is typically the independent variable or the explanatory variable, and then Y would be the response variable or the dependent variable, right? So I need to pick a lane. I need to pick one name that I refer to them. So I'm not always saying the double ones, but maybe it's good to have all the double ones. Redundant, but good. So the difference between the variance and the covariance is that now we're combining the distances of the X's from the X bars, as well as the distances of the Y's from the Y bars. So in terms of our calculation here, what we would have is we would have our column of X's and our column of Y's. For example, if I grab this data set here, whoops, copy. What we would do and what we would have is the high temperature was our X and the bottled sales was our Y, right? So in terms of what we would do to calculate the covariance, if we were doing it by hand, even if we're doing it by hand in Excel, right, that's fine. I just mean if we have to work out this formula by ourselves. But of course, there's built-in functions in both Excel and R and whatever else you want to use. But so first, you need to make a new column of the X, each X minus X bar, right? So that looks familiar from the variance, right? But then when we had the variance, we had to square each of those values, add them up, divide by n minus 1, take the square root. So we're going to do things a little bit different here. So this would be, now I don't have the mean of these numbers, right? But it would be 78 minus the average of these numbers, 79 minus the average of these numbers, and so on and so forth. So 78 minus X bar, 79 minus X bar, blah, 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 blah. Then I would make another column. And that's just because I like to break it down into tiny itty bitty increments, right? Because I don't want to find this distance and then multiply it by another difference and then add them up. That's just a lot of steps for me to do in one go, right? But here it would be 23 minus Y bar, 22 minus Y bar, so on and so forth. Where Y bar is, of course, the average of the Y's now, right? Which means we'd have to add these up and divide by, I'm guessing 14 summer days, it looks like. Then I would make another column of X minus X bar times Y minus Y bar. So now I would take this value times, and I've got it all kind of jumbled here, sloppy. Right, I would take this value, so let's call this A, and let's call this result B. Right, then I would have A times B. Okay. At the bottom here, I would add these up to make the sum of X minus X bar times Y minus Y bar. So it's a little bit different because it's it's really different. It starts off the same, right? It still wants to know the distance of each point from the mean, but then we multiply it by the distances of the Y's from the mean at that point, right? So because these are coordinates, right? 78, 23, right? So we have to use them pairwise, and then we add those up, and then we divide by n minus 1. So, and the n minus 1, like I was kind of mentioning, I haven't looked into the covariance exactly, but I'm guessing it's the same explanation as why we do it for the standard deviation, which is that it's just an attempt to get a better estimate for the population. Right here, we're kind of zoned in. If we just divide it by n, the estimate ends up being too close to the sample means as opposed to the population means, but that's kind of beyond what we're doing here. So hopefully you're just okay to accept it and take my word for it. I know. No one wants to do that. You have to. The difference between the covariance and the variance is the variance is just for one variable, right? So it's just for one x, right? Whereas, so we could look at the variance of the high temperature, or we could look at the variance of the bottled water sales, but in order to combine them to see how they change together, that's when we need the covariance, right? And so the covariance measures the variability, right, within the pairs. Sorry, this fly is driving me nuts. I need to get one of those like zappers for this one fly. Maybe I'll just shoot him.
Do you have a fly swatter in your house?
No, I think I will soon though. It's a quick little guy. Gotta get him. So anyways, so the covariance, right, is measuring the covariance, can we show it on a graph? Yes, sort of. To be continued here. I'll just bring in that graph because maybe that'll make it more helpful. Copy. I almost deleted it. I guess I could shake it to undo or something. Okay. So here, just for a visual, if we have a positive covariance, right, then we're going to have something like this, right? So notice that we've got kind of this strip of information, right? So all the data is kind of changing together. So as X is increasing, our Y's are also increasing, right? And then if we move in the negative direction, right, as X is decreasing, then our Y's are also decreasing. So in general, this relationship, we say we have a positive relationship. And what we see then is that the covariance is also positive. Okay, and so here we have a positive relationship, positive linear relationship. It's good to get in the habit of calling it a linear relationship, right? I will show you one where we don't have a linear relationship, but then you can just call it a non-linear relationship for now, right? There are other models that we'll introduce slowly. Okay. So here, if the covariance is approximately 0, it just means that X and Y are not linearly related, meaning that you would have something that looks like this. Notice that you could fit a line like this. So a line of best fit like this, you could fit it like this, you could fit it like this. And it doesn't really, change anything. So when you're just floating around in a cloud here, how that's numerically shown is that you have a covariance of approximately 0, right? And so there's no clear path for the relationship. Okay. And so here, the negative relationship looks, of course, similar to the positive relationship, except it's going down, right? And so now as my x's increase, my y's decrease, and as my x's decrease, my y's increase, right? So I've got this general path that it's following. And so I'm going to get a negative covariance. And this is just a negative linear relationship. Okay. So the covariance measures just kind of the basic way to think about it is that the covariance measures how closely the points follow some path. Okay, so here I'll write that here. The covariance measures how closely the points follow a certain path, right? A certain linear path. How closely points follow a linear path. One major problem with just using the covariance is that the covariance is going to depend on the units of x and y. Okay, so one major problem we face when using the covariance is that the covariance SXY depends on the units of x and y. Just for clarity there. So is that the covariance depends on the units of x and y. For example, I'm 5'7". 5 feet times 12 is 60 plus 7, so I'm 67 inches, right? But I'm also 170 centimeters. So you can see how the magnitude of 170 centimeters, right, is going to change the covariance. And so, right, I've got larger numbers when I'm working in centimeters versus when I'm working in inches, right? And so that's a problem, because that means that a huge covariance doesn't necessarily mean that there's a strong relationship, right? And so as an example, I hope I did the math right. I'm not that good at inches and feet and stuff. So I am 67 inches tall, or 170 centimeters. It's actually 171, but let's keep it simple. Right, and so the units here would impact the covariance on, and same thing, if I'm declaring my weight, I won't take it that far, right? But if we're thinking about weight in terms of pounds versus kilos, now pounds, right? I would weigh more in pounds in terms of a number than I do in kilos, but my weight is the same, right? And so it depends on the units. So that's why we use the correlation instead. So I just want to finish this quick example here. So the covariance would be larger when measured in centimeters meters, anyways, than inches, right? And so to avoid that and to kind of remove that, we talk about the correlation. And so to avoid the dependency on units, we typically use the correlation as a measure of the strength and direction of a linear relationship, as a measure of the direction and strength of a linear relationship. It uses the covariance, so we need the covariance in order to get the correlation. So let me just grab it here. So it's called the correlation coefficient, but typically, well, I mean, technically it's called the Pearson correlation coefficient, but we usually just call it the correlation. So the correlation coefficient, or the correlation, is denoted by a lowercase r, and usually we don't really use the subscript xy, right? And so, or just r. Okay. But R is the sample correlation coefficient. And so R, the correlation, C was probably taken for something else already. They didn't have all of math and stats mapped out, so they kind of ended up using weird variables sometimes. But R is the correlation. And notice that it has the covariance as the numerator, right? And so what it's doing is it's taking that covariance, which is a measure of the relationship, right? But then in order to essentially divide out the units, we divide by the standard deviation of x times the standard deviation of y, and that's what makes it unitless. And so here you have the covariance. And then you have S standard, hey, it's right here. But I do want to keep that first one, but the other two are down here. So S subscript X is the standard deviation of X, whereas S subscript Y is the standard deviation of Y. Now, in terms of if we have a data set, right, each variable, oops, sorry, it's catching up. Each variable, we can calculate the mean, we can calculate the standard deviation, right? And so now when we have two columns, we have a standard deviation of X, but we also have a standard deviation of Y, right? And so we need some way to denote those. And I only bring that up because a lot of people are thrown off by this SX. It's catching up again. Hello? SX and SY. It had caught up. I just wasn't caught up. Right, and so SX is just this for your X variable and this for your Y variable, right? And that's that. Okay, so we said that the correlation is a measure of the direction and the strength, oops, of a linear relationship. Okay. And so in terms of the direction, well, we said that the covariance, if you have a positive relationship, is going to be positive, right? We also established last day or the day before that the standard deviations have to be positive, right? And so both the standard deviation of X and the standard deviation of Y are always positive, right? And so we're always dividing by a positive number. And so what that means is that if we have a positive relationship, then the covariance is positive. So then our correlation is going to be positive. Whereas if we have a negative relationship, the correlation is negative because then the covariance would be negative divided by a positive value, right? And so that's how we get the direction of a linear relationship from the correlation. So I like to do this kind of number line style, because as a fact, correlation goes between -1 and +1, right? And so we're stuck here, -1 and +1, and here's our correlation. Here's 0. So if we have a negative value, then we have a negative relationship, right? And so here, negative relationship. So it would look something like this, right? A negative relationship. And remember, it has to be a linear relationship. So it has to be for a straight line. Versus between 0 and 1, right? Now I'm talking about positive values. So now I have a positive relationship. So in general, I'm going to have something that looks like this, right? Now the strength is going to move from 0. So let's say I'm talking about a positive relationship. What's going to happen is that, so a correlation of 0 comes from a covariance of 0, which we saw, right? A covariance of 0, let's see if it's keeping up here. Because 0 divided by anything is going to be 0, right? And so if the covariance is 0, then we have this kind of cloud. There's no true relationship here, right? We could angle our line any which way and it doesn't really capture anything, right? And so here, this would be a correlation of 0, okay? Then when I move out towards a correlation of 1 or -1, then I'm moving out towards just a stronger and stronger relationship. Okay. So here, right, the strength increases as we move in either direction. Right. Typically, and it depends on the data that you're looking at, but if you're not expecting a huge relationship or kind of a really strong relationship, it might depend on what you're looking at. But typically what we consider is kind of roughly here at -0.5 and positive 0.5. Anything from 0 to roughly 0.5 in either direction, we would consider weak, right? And so basically anything here, I would call it weak, right? And we could call it things like very weak, moderately strong, right? And so there's a lot of terminology that we could, and it just depends on, what you're looking at. But then as we move out here, right, I would call it this a strong positive linear relationship, or on the other end, I would call this a strong negative linear relationship. And notice that there's some curvature here in the cutoff points. It's not exactly at 0.5, right? It just depends on what you want to push for, right? And so the correlation, it's important to remember that it goes from -1 to +1, and a relationship that has a correlation of +1, for example, well, that would be where all the points are exactly on the same line, right? So there's no variation if you're at +1 or -1, right? Because then they're just all on the exact same line. But as soon as you have a little bit of scatter around there, then you're going to move kind of in towards 0, depending on how much scatter. Just as to give you a rough idea, for something like this one here, this correlation, if I had to kind of guess, this would be around probably 0.8, 0.7, 0.8. This looks really strong. Basically what happens is as soon as you see some sort of relationship, you've passed that 0.5 threshold. So until then, it's really hard to see anything happening distinctly. So this would be considered very strong. All right. Good. Okay. Good. So the correlation is really important, right? Especially if we're talking about, the direction and the strength of a linear relationship, and we don't want to have to worry about units, right? Now, all of a sudden, it doesn't matter what units I measure my height in, right? The correlation is going to stay the same. And that's good because my height didn't change, right? So I feel like there was another one here. Oh yeah. I've got this in here, so you can refer to that if you want to, but it's basically what I just wrote out. So I'm gonna leave it here, but I do want to show you this one here. So copy, sneak attack. So here, notice that we have a non-linear relationship, right? This is a relatively strong non-linear relationship, right? Because we can see that there is some pattern, and we expect future data points to follow this pattern as well, right? Just that's what it looks like. So here, all right, we've got this kind of strong non-linear pattern. Okay. What happens is that, okay, we have an X and we have a Y, right? We have an X, which is the outside temperature, and we have a Y, which is the dollars spent on environmental control. Fine. Okay, so we could calculate the correlation here, right? But what's going to happen is that the correlation is going to be approximately 0, right? So the correlation would look at the straight line model of this data. So what the straight line would try to do is it's trying to capture as much as it can. And I would guess that the straight line model would end up looking something like this, where it's trying to kind of do its best to capture all this activity, right? But because it's nonlinear, it's not a very good model, right? You could use this straight line to predict future values, but for values of X up to 40, it would underpredict. And then between 20 and 60, it would overpredict. And then it would underpredict again. And it never does a good job predicting, right? And so here, the correlation would be approximately 0 because none of these points are close to the line. Right. And so we can calculate the correlation for any relationship, but it is only useful for a linear relationship. Okay, good. Okay, that's a good start for more than one variable. Any questions about the correlation before I start about missing data and stuff like that? Keep an eye on the chat, but it's basically where I'm leaving it, so that's good. All right. So the next section and the last section of chapter 2 is about data cleansing. So how do we clean data? Usually when we get data, we need to clean it, we need to massage it, we need to wrangle it, right? That's the name of this course, is data wrangling, because usually what we have to do is we have to kind of massage the data or wrangle the data if you're kind of more aggressive, I guess. But it's fun to say data wrangling, right? Is you have to kind of get the data to into a form that works for your analyses. And so the hard part is knowing what's going to work for your analyses, right? And so sometimes you need to kind of change the shape of the data, right? And so we can do things like flat data, long data, but we'll talk about that later. But for now, I want to focus on missing data. So when we first get a spreadsheet of data, and let's just stick to a spreadsheet scenario, right? If you've got big data, there's no way that you can look at it all, right? And so let's just assume that you can look at the data for now, because it makes the most sense. So I send you an Excel sheet, you open it, and you see that there's missing data, right? That's going to be a problem, right? Or you maybe do some analyses and identify some outliers, right? That's also going to be a problem, and you need to figure out how to deal with that. Okay, but for now, let's focus on that missing data. So missing data can come in different forms, right? So how is the data missing? That's going to be important. And so how we treat the missing data depends on how the data is missing. So we're going to talk about how is the data missing. And there's subtle differences that I want to point out. So it's this long blurb, and I couldn't help it. I just included all of it, but I'll do a little summary of these blurbs here. Oh. Talk about this one first. So the first thing that we do when we have missing data is we've got two paths, right? We could have legitimately missing data, meaning that there shouldn't be an answer, right? And so they had the example of, oh yeah, it's here. So let's just use it. Do you belong to a fraternity or a sorority, right? Was the previous question. And then if they said no, then they can't answer the next question that asks, how long have you belonged to this sorority or fraternity, right? And so that would be legitimately missing. Now, we try to avoid that scenario when you're building a survey, right? Then you should have a not applicable option in that case, right? So you only get legitimately missing data if you make a bad survey. So that's on you. But then you have to go back and you have to look, okay, should this be missing? Should it not be missing? Right. And so legitimately missing data, we often try to avoid this by including a not applicable option, right? Often you can capture that legitimately missing data by having another option that people can click. Okay, and so not applicable is the most common, right? But if you forget, then you'd have to go through and look at, okay, was the previous answer no? If the previous answer was yes, I do belong to a sorority, in my case, right? And then I didn't answer the rest, right? The next question, how long have I belonged in that sorority? Then we call that illegitimately missing data. Okay? So you've got kind of legitimately missing data and illegitimately missing data. Illegitimately missing data is going to be more of a concern. So it could be for a number of reasons that you have illegitimately missing data. So for example, if I said, yes, I belong to a sorority, and then I didn't answer the next question, what's the reason that I didn't answer the next question, right? How long have I belonged to that sorority? Does it depend on another variable that I've already answered, right? Or does it depend on the number that I'm about to give you, right? And so those would be two scenarios, two different illegitimately missing data scenarios. Or did I just forget to answer? That would be another illegitimate missing data option. And so we talk about missing completely at random. In that case, it would be, okay, I just didn't enter something. There's no reason, right? Missing at random, maybe I didn't enter it because I felt that it was too related to another variable that I already answered, right? Or missing not at random would be, I don't feel comfortable giving you the amount of time that I have been in the sorority. Right, seems like a weird example, but there's more examples in that huge blurb that I gave you, right? But in terms of illegitimately missing data, so let's do a little tree here. If we have missing data, we could have legitimately missing data. Right, and so probably a not applicable option should have been given, right? But the respondent let's just think about it this way. The response would be not applicable. Let's just think about it that way in general, right? If there was a not applicable option, then that would be the response. Okay, that would be the only way that you can have legitimately missing data. Illegitimately missing data comes in 3 forms. Okay. Try to keep them. Actually, I think I'm going to need more room here, so I'm going to spread out just a little bit more. Missing completely at random. MCAR. Completely at random, it just doesn't depend on anything else in the data set. Okay. So missing value does not depend on any other value in the data. Question? Oh, maybe. Did you have a question? Anyone? No? Everyone's back on mute. Okay. Okay, so missing completely at random. It's just, it happened, right? There's no rhyme or reason why that happened. Okay. Missing at random MAR is maybe it's related, so maybe that missing value is related to another value in the data. Okay. So then the missing value is related to another value in the data. Now, the example that they have in the blurb is that maybe there's some diagnostic measures that haven't been included. So if you're a doctor and you've got kind of maybe a clinical trial and you're trying to decide if people should be in the study or not be in the study, maybe if the decision was that they're not healthy enough to be included in your study, right, then maybe you don't include all their diagnostic tests, for example, right? So then the data for the diagnostic tests is missing because they weren't suitable to be in the study, right? Which would be another variable, right? Should this person be in the study or not? Okay. So then that missing value is related to something else happening in the data, right? Or maybe something else related to that person. Right? Usually we're talking about people. And then I think it's missing not at random. Let me just confirm. Yeah. So missing not at random. MNAR, MNAR maybe, just for fun. So this is kind of the worst possible missing data point, is where someone refuses to give you an answer because of the answer itself. right? And so they've used kind of a low-key income category, right? And so as an example, so maybe people aren't reporting their income category because they make more than usual or maybe less than usual, right? And so, but definitely if we're thinking about kind of maybe a clinical trial scenario, if the data is missing for, you know, maybe, I don't know, some disease status, do you have COVID or do you not have COVID? If it's missing because they have COVID, then that's a problem, right? And so that would be missing not at random because that person was not, didn't want to say because of the actual response, right? And so the missing value, I'll write it down here. Wait. The missing value is related or is due to the response itself. The response itself, right? So if someone didn't answer a question because of what the answer would be, that would be missing not at random. And you need to kind of figure out how to deal with that, right? What's the hardest part, okay, so these are all definitions, blah, blah, blah. The hardest part as an analyst is that we don't actually know which one of these. It's not like there's another box. Hey, are you not answering this because you're not comfortable giving me the answer or because it just didn't apply to your situation, right? And so that's the hard part, right? And so there's going to be multiple ways that we can deal with missing data. So some of the ways that we can deal with missing data is, well, we could remove that whole row, right? Maybe we remove that whole person from our data set. That's going to impact our sample size, right? Or maybe we remove that variable, right? Maybe there's another variable that we could use. So then we can remove that column and we can still kind of get the same information from another variable, maybe. We could figure out a fancy way to impute the data. So to say something like, oh, I'm going to fill it up with the average of the remaining numbers, just so you have a value in there, right? And then go from there. There are more sophisticated techniques, but those are kind of the core three things that we consider. And so I'll end it there, but what I want you to do is just go through, here we talk a little bit more about outliers, but I brought this up, the outliers in the beginning, so you can read that. And feel free to read these examples because it is hard to kind of wrap your head around the first time around. And then the last thing that is in here is that it's common that we need to reduce the number of variables in a data set. And so then we need to consider how can I replace one or maybe three variables with one variable, right? And that's dimension reduction. But that's just a side note, so I'll leave it at that. So we're going to start chapter 3 on Friday, and I'm working on the notes, so I'll post those this afternoon. And if you have any questions, let me know. Otherwise, I'll see you on Friday. Stop this here.
All right.
See ya.